The second unique function of the liver is that it is the major site for cholesterol synthesis, starting with acetyl-CoA. The liver can ultimately determine how much cholesterol is produced in the body. The outcome of cholesterol production by the liver will have two other important effects. The first one is that the liver output of cholesterol will ultimately determine the plasma levels of cholesterol. And the second one is that the liver can serve as a major storage site or depot for cholesterol by its ability to convert cholesterol to cholesterol esters and store it in specialized lipid vesicles. Cholesterol biosynthesis in the liver is tightly regulated and is dependent on the rate-limiting enzyme in the liver, hydroxymethylglutaryl-CoA reductase, or HMG CoA reductase. There are several ways where HMG CoA reductase activity is regulated. The first one is that cholesterol can inhibit this enzyme directly as a feedback inhibitor. Also, mevalonic acid, which is the product of HMG CoA reductase, can inhibit this enzyme competitively as a feedback inhibitor. A second way cholesterol can regulate the activity of HMG CoA reductase is that the concentration of cytosolic cholesterol inside hepatocytes can regulate the gene expression of HMG CoA reductase in the liver. High concentrations of intracellular cholesterol will downregulate the gene expression of HMG CoA reductase, and conversely, low intracellular cholesterol will upregulate the gene expression of HMG CoA reductase. A third regulatory mechanism of HMG CoA reductase in the liver involves the hormones insulin and glucagon. Insulin can promote the dephosphorylation of HMG CoA reductase through stimulating a phosphoprotein phosphatase. The outcome of this covalent modification is to activate the enzyme. On the other hand, glucagon can promote the phosphorylation of HMG CoA reductase and consequently inhibit the enzyme. HMG CoA reductase can be specifically covalently modified or phosphorylated by the protein kinase AMP kinase, and that also results in the inhibition of the enzyme. In addition to cholesterol being able to regulate the gene expression of HMG CoA reductase, high intracellular cholesterol can regulate the degradation of HMG CoA reductase in hepatocytes. High intracellular cholesterol concentrations will promote the ubiquitination of HMG CoA reductase, which is an important signal to send HMG CoA reductase to the proteasome, where it will be degraded, and as such it will be removed from the cytoplasm of hepatocytes, resulting in decreased cholesterol biosynthesis. As mentioned before, ultimately the amount of free intracellular cholesterol will determine the amount of plasma cholesterol. Low intracellular cholesterol will increase the gene expression of the LDL receptor on the surface of hepatocytes. When there are more LDL receptors on the surface of hepatocytes, more LDL particles can be endocytosed from the plasma, thus reducing their concentration and eventually reducing the total amount of plasma cholesterol. In fact, this is the therapeutic strategy behind the use of statins to reduce plasma cholesterol. The inhibition of HMG CoA reductase by statin results in a decrease in intracellular cholesterol concentration, which in turn results in an increase in the gene expression of the LDL receptor. More LDL receptors on the surface of hepatocytes will endocytose more LDL from plasma and thus reduce plasma cholesterol. The third important function of the liver in terms of cholesterol storage is that it has an enzyme abbreviated ACAT, acyl-CoA cholesterol acyl transferase, which is the enzyme responsible for converting free cholesterol into cholesterol esters. Cholesterol esters, once formed, can be packaged and stored in the liver. By esterifying cholesterol and packaging it in special storage vesicles, ACAT can contribute to the reduction of free intracellular cholesterol within the liver. Stored cholesterol esters in the liver can be later used for the liver's own metabolism, such as the synthesis of bile salts.